So in the previous lecture, we ended our lecture with an example from group theory. So we saw that given a group and given a normal subgroup, we can look at the equivalence classes. So the normal subgroup defines an equivalence relation on our group, and we can look at the equivalence classes. We can give the set of equivalence classes a group structure such that some nice things happen. And today in this lecture, we will see that we can do something similar in topology. So let's address the question first, what the question is. So let X be a set, and suppose we have an equivalence relation on X, right? So let X mod equivalence be the set of equivalence classes right. So then we have this obvious map, the natural map pi from X to X mod equivalence, right. What does it do? It takes X and sends it to its equivalence class. So right now everything is only happening for sets, right. Now suppose we have a map of sets f from X to Y, right, such that X equivalent to Y implies f of X equal to f of Y, right. Or this property we can phrase it as follows, simply stated: f is constant on equivalence classes. Right. So then this function, this map of sets, it factors uniquely as so we have f X mod equivalence is pi, so it factors like f naught. We get a map of sets from the set of equivalence classes to Y, right? And what is f naught? So f naught is defined as follows: right. So let alpha be an equivalence class, right, and let X in X be such that the equivalence class of X is this alpha, right. So we define f naught of alpha to be equal to f of X, right. Now this is well defined because f is constant on equivalence classes, right. So clearly this definition makes sense as f is constant on equivalence classes. Right. So now we are going to bring in topologies and we are going to complicate this problem. So now further assume that, or rather now consider the situation where X is a topological space and we have this equivalence relation on X, right. So is this an equivalence relation on the underlying set. Okay. So what we want to do is we want to put, so the question is, can we put a topology on X mod equivalence? So this is just like, can we put a group structure on G mod n such that the following two things happen. One, the map, the natural map pi from X to X mod equivalence is continuous, and two, okay, suppose we are given a continuous map, f from X to Y. So Y is another topological space and we are given a continuous map such that f is constant on equivalence classes. Right. So then as a map of sets, we are going to get a factorization like this. F is this, we have pi, we have X mod equivalence, and we get this map of sets F naught. Then we get a map of sets F naught from X mod equivalence to Y. Right. So the second condition we want is that F naught must be continuous. Right. So we do not, so we get a unique map of sets in fact. Right. Even here the F naught is unique. It's and completely determined by F. Okay. Okay. So let me make a remark. Right. So if you only impose condition 1, so then this problem has a very easy solution. Right? Easy solution, namely, we can just give X mod this equivalence relation, the equivalence class is the trivial topology. Right. So since there are only two open subsets, the empty set and the entire set, the inverse image of both these will be open and therefore pi will be continuous. Yeah. But if you give this the trivial topology, then the second condition, the second property may not be satisfied. Okay. So the main result, the main theorem we are going to prove in this lecture, there is a unique topology tau on X mod equivalence which satisfies the above two conditions. Okay. So let's prove this theorem. So proof. Let us first show that there is such a topology tau on X mod this equivalence with satisfying the two conditions. Okay. So we are going to define tau first. So let tau be the collection of subsets U contained in X mod equivalence such that this pi inverse U is open in X. Okay. So it is easily checked, and I will leave it as an exercise. That tau satisfies the conditions to define topology. On X mod equivalence. Okay, that's a very easy check, and I will leave it as an exercise. Yeah. So obviously, so now let's prove that both these two conditions are satisfied. So first we have to show that this map pi from X to X mod equivalence is continuous. Yeah. So 1, the map pi X to X mod equivalence is continuous, right? For this we have to show that given an open subset V in X mod equivalence, pi inverse V is open in X. Yeah, but this is clear from the very definition of the topology on X mod equivalence. From the definition of tau, right? V is in tau if and only if pi inverse V is an open subset of X. Okay. The second condition we want to check is, suppose we are given a continuous map f from X to Y, which is constant on equivalence classes. Right. So then we get this resulting map f naught of sets, a map of sets determined by f, right. So we need to show that f naught is continuous. Is continuous, right. For this we need to show that, so let V contained in Y be an open subset. So we need to show that f naught inverse of V is open X mod equivalence. Yeah. So for this, applying the definition, of tau, this happens if and only if pi inverse of f naught inverse of V is open in X, right. But simple set theory tells us that pi inverse of f naught inverse of V is equal to f inverse of V, which is open as f is continuous. Okay. So this shows that tau satisfies both the conditions. Okay. Next, let us prove that this topology is unique. Right. So suppose there is another topology tau prime on X mod equivalence such that conditions 1 and 2 hold for tau prime. Okay. So let's make this diagram. So we have X, we have this map pi. This map is to X mod equivalence comma tau prime. Yeah. So the first condition is that the obvious map x goes to the class of x. This should be continuous if x mod equivalence has the topology should be continuous in our topology. So we are giving x mod equivalence the topology tau prime, and by assumption, since tau prime satisfies condition 1, this map is continuous, right? So, but we also have this map x mod equivalence comma tau, right? Now, as tau satisfies condition 2, we get this dotted arrow like this, right? So let's call this pi naught, yeah. Okay, so the dotted arrow we will get anyway, so note that the map of sets pi naught is forced to be the identity as this, yeah. Right. So this map of sets pi naught that we get, that's supposed to be the identity, right? So since tau satisfies condition 2, this implies that pi naught is continuous, right? So thus, if V is in tau prime, V is an open subset in tau prime, then pi naught inverse of V, which is equal to V, is open in tau, right? So this implies that tau prime is contained in tau. Okay. So similarly, we can switch the roles of tau and tau prime. So we have this, right? So we get this pi naught, right? So as tau prime satisfies the second condition, this implies that pi naught is continuous. So once again, this implies that tau is contained in tau prime, right? So thus tau is equal to tau prime. Okay. So this completes the proof of the theorem. So this topology, the above topology on x mod equivalence is called the quotient topology. So we will end this lecture here.